Welcome to my channel, Tech Talk with Nathan. Today we are going to talk about Kubernetes secrets, how you manage secrets in Kubernetes. Secrets are one of the hardest problems in Kubernetes. Passwords, API keys, token, certificates, they all need to be secure or rotated in Git. In this video, I will explain the main secret management approach in Kubernetes, how they fit into GitOps, and why Vault is my preferred solution. I will keep this conceptual. The demo will come later. So what are Kubernetes secrets? Kubernetes provide a native secret object to store sensitive data. But by default, secrets are only base 64 encoded, not encrypted. That means that if someone can read them from etc, the API, or Git, they are exposed. With GitOps, Git is the single source of everything like deployment, config, infrastructure, etc. live in Git and is reconciled with the cluster. But secrets don't belong in Git in plain text. So we need patterns that let us stay security without exposing our sensitive data. So I will be covering the main approaches of secret management. The first one is seal secrets. Seal secrets encrypt Kubernetes secrets using a cluster-specific public key with the sensitive data in your development environment. It can be on your laptop. You use KeepSeal to seal the secret. You commit the encrypted version to Git, and only the cluster can decrypt it because only the cluster have the private key. So the benefit of using seal secret are it's GitOps friendly, simple. Some inconvenience are mainly the fact that it's tied to a specific cluster. Rotation and multi-cluster setups can be very painful. The next one is external secret. External secrets pull secrets from an external backend. It can be a cloud secret manager like AWS or from Vault, and it creates Kubernetes secret at right time. Benefits are there's no secret in Git, and it's centralized, and you can manage centrally from any cloud manager. But the problem is it requires an operator, and also that you need to sync secret into Kubernetes. You are still creating secret in Kubernetes. The next one is secret store CSI driver. It mounts secret directly into pods as files without creating Kubernetes secret object at all. Benefits are secrets never hit etcd. It's great for strict security environments, but the inconvenience are your app must read secrets from file system, and it can be more moving parts. The next one is SOPS. SOPS encrypts your secret value directly in YAML file using KMS, GPG keys, or any other cloud keys, and then store in Git encrypted files. Argo CD or Flux CD decrypts them and deploy. The benefits are it's Git native and it works well with customized, but the problem are that you need to manage the key and you have to rotate it manually. The next one is HashiCorp Vault, which is my preferred solution, mainly because it's cross-platform and cloud agnostic and extremely flexible. Unlike specific secret managers, HashiCorp Vault the same on Kubernetes, on bare metal, on any cloud, in multi-cluster and hybrid environments. Vault isn't just a secret store, it's also a full platform. With Vault, you have dynamic secret, rotation leases, auditing, and fine-grained access control. In Vault, we have different ways we can use the secret manager. The Sidecar. The Vault agent injector injects secret directly into pod at runtime. How it works, the Sidecar authenticates to Vault using the pod service account. It fetches secrets and renders them into a shared in memory. Then your application just reads files. From the point of view, your app Vault unaware, but it still gets secrets. The strength of this method is it's strong. It supports dynamic secrets like DB credentials, AKIs, certificates, and many more. You can automate renewal and rotation. Secret never attach etcd. It uses Vault agent for templating, caching, and auto authentication. The trade-off are it's one extra container per pod, more moving parts, and secret are file-based. The next one is the Vault Secret Store CSI drive provider. Here, secrets are mounted directly into pod as files using a CSI volume. Secrets are fetched before the container starts. Pod startup is blocked until the secrets are available. So the key point here is there's no sidecar, but secrets are still injected at runtime. The strength: no extra container, clean file system integration, can optionally sync secrets into Kubernetes secret. It works well with legacy application, but the trade-off: no templating or caching. There's a limit rotation support, and it uses host path, and some platform might be supported. The next one is Vault Secret Operator. It syncs Vault secrets into Kubernetes secrets using custom resource definition. You define the custom resource definition, like, for example, Vault Dynamic Secrets. The operator fetches secrets from Vault. It creates and updates Kubernetes secrets. It handles rotation, and it can trigger rolling restarts. The key point here is this is the most Kubernetes native Vault integration. The strength: you have a perfect fit for GitOps. It uses native Kubernetes secrets. It supports rotation, rollout automation, and it's strong governance observability. But the trade-offs are: secret exists in etcd, encrypted but still there. It's less suitable for ultra-sensitive secrets, and you have operator dependence. So let's compare these three integration methods. The first one, the sidecar, is better for runtime secrets, and credential and minimal app change. You don't want people to touch the configuration files. The second one is the Vault Operator. It's best for GitOps, Kubernetes native workflows. And the last, not the least, is the CSI provider, which is best for file system-based secrets. It's simpler. There are other methods of integrations, like external secret operator that we have already mentioned. Here, Vault will be used as a backend via standard external secret. And the second method is a direct API integration, where the applications fetch secrets directly from Vault. And the last one is from Argo. You can have a Vault plugin where Argo renders manifest using secrets, fetching them from Vault. In this case, the secrets are not stored in Git. To summarize, in this picture, you can see all the difference between the sidecar, the CSI, and the Vault Operator. Kubernetes gives us primitive. GitOps forces us to think carefully. There are multiple valid approaches, and Vault stands out for cross-platform and production-grade secret management. In my next video, I will do a demo with Vault in a real Kubernetes environment with GitOps setup, so that you can see how this works end-to-end. We will be using Vault Operator. If this is useful for you, like, subscribe, and I will see you in the next one.